This video will continue our discussion of line integrals in conservative vector fields. So using the given potential function, they actually gave it to us. Of the gradient field f and the curve c to evaluate the line integral. There we go. Okay, so let's go ahead and let's just find f. F is our gradient of phi. So that's going to be y comma x. So we have that. I'm actually going to put that down here. We have plenty of room. We have phi here. Let's look at our definition that we're working into. We know that the gradient of phi is equal to f. That's what they told us, right? That's where we're starting. And we know by that theorem that the video before this is equal to f dot dr is the same thing as our potential of like our B point, our top point, minus our bottom point. All right, so in this case, I need to work to that potential function, but I really need it terms t, since my path is in t and the boundaries are in t. So I'm going to replace this. We get x equals cosine t here, and we also get y equals sine t. So we go replace this vector. Cosine is, or y is sine in this case, and then x is going to be cosine t. That's just grabbing what we just wrote down. And I'm going to take that now. I have f, and I also want phi in terms of t, because I'm going to plug in my t's in a moment. Okay, phi of, and then I just replace what x was. Okay, that's cosine of t, comma sine of t. And we're going to plug that into xy. Okay, I get sine t, cosine t, or whatever you prefer. I don't know why I flipped it that way. All right, so I have that function. I know that's what phi is. And I know that our path is going to run from 0 to pi. So this function, this line integral over path c that they defined for us, f dot dr, is equal to, and it's just going to be my phi of, and I'm just going to plug this in because we could really change this. We don't have to have, we could just do phi of t is equal to sine t, cosine t, because that's all we have to plug in. So plugging in now my t's, it's going to be pi minus phi of 0. We're going to have to find this potential function, and I feel like that method makes a lot more sense. But in this case where they gave me phi, all I have to do is put phi in terms of t, find my bounds. I really didn't even need the vector field. I was just wanting to write it down so we know we're still working with one. So I just have to plug this in. All right, well, we do sine times cosine. We're going to get sine of pi, cosine of pi. You're going to see how this works out. Sine of pi, cosine, these should be 0. My mind is already focused on the answer afterwards. That all zeroes out. So whatever this means in this case, going from 0 to pi, it goes to 0. But we can use the potential functions to get there. We know our path is not circular. If it was 0 to 2 pi, it'd be all the way around. So this isn't based on the conservative idea of going from one point to another point, which we'll talk about more here in a moment. But as this sits, we have a 0. All right, cool.